So, in this class, we will start the mixed integer programming problem. So, basically you are having the linear programming problem. If you see your linear programming problem, the decision variables can take any value, any real value which we are saying x j greater than equals 0. Now, from this linear programming problem, you are formulating integer programming problem. In integer programming problem, what happens? The variables x j are greater than equals 0 and they are integers. Now, another type of problem which may come, that is which we call as MIP, mixed integer programming problem, say mixed integer programming problem. Here also your x j will be greater than equals 0, but some x I be integer and some x j are real values. That means, here x j can take either integer value or real value. This type of problems we call it as the mixed integer programming problem. So, basically if you see, initially we started with the linear programming problem, then we have done the dual simplex methods. Now, we are saying that from I may have a special type of linear programming problem which we call as integer programming problem, where all the decision variables are positive, that is greater than equals 0, and integers only. We have seen how to find out the solution, and the mixed integer programming problem, where x j decision variables will be greater than equals 0, but some x j may be integer, some x j may be real. This type of problem we call it as mixed integer programming problem. So, if only a proper subset of decision variable in an LPP is restricted to be integer, the problem is known as mixed integer linear programming problem. So, if some of the subset of the decision variables restricted to integers, other variables may take real values. What are the steps? Steps are solve the LPP without integer restriction first. That means, as if you do not have any restriction on it. By that way, you try to solve this particular problem, as we have done earlier. Step 2, if all variables are integer valued, or at least integer restricted variables are integers, then optimal solution is achieved. Otherwise, go to next step. What do you mean by this step 2? If all the variables are integer valued, then obviously your optimal solution is your feasible also, because all are integer valued, because we have told some variables will be integer, some may take real value, some may take integer value. And if at least integer restricted variables, that is the variables whose values should be integer, in the optimal solution their value is becoming integer only, then the optimal solution you obtained in step 1, that is the optimal solution of the original problem, and then you terminate. Otherwise, you have to go to the next step. In step 3, this is just like your Gomorian cutting plate method, what we did the first one, that is IPP problem. So, here you choose the largest fraction of basic variable, choose the largest fraction of basic variable that is restricted to be integer. Let it be f k 0 for the variable x b k. So, whenever you are coming in step 3, the meaning is that your some of the variables are taking non-integer values which should take the integer values. So, out of those variables which are taking the non-integer values, you choose that variable, basic variable which has largest fractional part, which has largest fractional part. So, we are assuming that if f k 0 be the largest fractional part, corresponding basic variable is x b k. So, once I am obtaining this one, then I am formulating the Gomorian constraint like this, that is summation j belongs to r plus y k j x j. This is summation over j belongs to r plus. I am writing here r plus equals j such that y k greater than 0, because whenever you have y k j values, that is in a table, whenever we are considering in a table y values you are taking, y values may be positive, y values may be negative also. So, r plus you are telling, whenever you are taking r plus, in that case you will take those j values where y k j will be greater than 0, and r minus will be those values of j where y k j will be less than 0. So, I am formulating it like this: summation over j belongs to r plus y k j x j plus f k 0. Again remember, this f k j is nothing but this largest fractional value corresponding to the variable x b k. So, f k 0 by f k 0 minus 1, summation over j belongs to r minus y k j x j. This must be greater than equals f k 0, where f k 0 lies between 0 and 1. So, if you remember, for integer problem, integer linear programming problem, this Gomorian constant value was little different, and for fractional part it is different. In the for the case of integer linear programming problem, I have shown how we derived this equation. Here, since we have done it, so I am leaving it to you that how we can come to this particular inequality. So, once I am obtaining this inequality, from this inequality I can write down the corresponding equality by adding the Gomorian slack variable g 1, which I am specifying. So, your g 1 is this one, that is minus f k 0 plus summation j belongs to r plus y k j x j plus f k 0 by f k 0 minus 1 summation over j belongs to r minus y k j x j, where g 1 is the Gomorian slack variable. So, by on this inequality constraint, we are this at first we are making the non-negative, sorry, this is already greater than equals type of inequality. This first we are making the less than equals type inequality by multiplying minus sign on both side of this. Then you are adding the Gomorian slack variable g 1 and you are getting this particular equation. So, now as usual you have to add this Gomorian constraint in the last row of the optimal simplex table. That is, last optimal simplex table, whatever you have derived earlier, for that one, for that last simplex table, you add the Gomorian slack constraint, and then you apply dual simplex method. Already I have explained, I have to use the dual simplex method because the basic variable which will be entered, the value of that basic variable will be negative. Therefore, to find the departing vector and entering vector, I have to use the dual simplex method, which we have discussed earlier, to find the optimal feasible integer solution. And once I have obtained it, then step 6, repeat the procedure until all variables, or I should say all required variables are integers. So, this I have to go on adding the constraints until I have the fractions, until I am obtaining the values of the decision variables as integers which are required. So, now let us take one example and let us see how we solve this particular problem. So, again I am taking a simple small problem. Maximize z equals x 1 plus x 2 subject to 3 x 1 plus 2 x 2 less than equals 5, x 2 less than equals 2, x 1 x 2 greater than equals 0, x 1 is an integer. So, basically here you see the difference is x 1 we are specifically saying it is an integer, and x 2 we are not mentioning anything, we have told x 2 will be greater than equals 0. So, x 2 can take real value as well as integer value. So, I have one variable whose optimum value should be integer, and I have another variable whose optimum value may be integer, may be real. So, for this problem, as we have told earlier in step 1, what I have to do at first? I have to solve the problem forgetting about the integer constraint. That is, first I will write this problem into the standard form. The standard form will be maximize z equals x 1 plus x 2 subject to 3 x 1 plus 2 x 2 plus x 3, this is equals 5. Next one is x 2 plus x 4, this is equals 2, x I greater than equals 0 for all I, and your x 1 is integer. So, here your x 3 and x 4, these are slack variables which you have used to make these less than equals type problems into equality problems. So, I have used this thing. So, at first I will formulate from this the initial simplex table. So, let us formulate the initial simplex table from here. Obviously, the coefficients in the objective function for the slack variables x 3 and x 4 will be 0. So, and in the basis 2 variables will enter, that is x 3 and x 4. These 2 will enter, because if I make x 1 x 2 as 0, your x 3 will be 5, x 4 will be 2. So, once I am doing it in the table, first table your x 3 and x 4 is appearing. Here I have y 3 and y 4. The values of the coefficients are 1, 1, 0 and 0. X 3, x 4 corresponding objective function coefficients are 0. Your b values for this particular problem is 5 and 2. So, once I am writing b values, b value is 5 and 2, and then you are having 3, 2, 1 and 0, 0, 1, 0 and x 4 is coefficient is 1. So, you are forming the initial simplex table. From the initial simplex table, now calculate the zj minus cj value. This will be 0 into 0 minus 1, this will be 0 into 0, 0 into 2 plus 0 into 1 minus 1. So, it will be minus 1, this will be 0, since 0 is there, this will be 0. Now, zj minus cj is greater than equals 0, zj minus cj for this case is less than 0. So, you can choose, both are having same value, any one you can choose, I am choosing say this one. So, x 2 will be the entering vector over here. So, since x 2 will be the entering vector, therefore, you have to calculate the ratio, that is 5 by 2 and this is 2 by 1 for this case, b value by y value. So, this gives the minimum value, therefore, your departing variable will be in this case is x 4. So, as usual whatever you have done earlier, your x 2 will be the entering variable in the basis and your x 1 will be the x 4 will be the departing vector, and the pivot element is 1, that means this is already 1. I have to make this component as 0 in the next table. So, in the next table x 4 will be replaced by x 2. So, once I am doing it, your x 3 will be replaced by x 2. So, here now x 3 x 2 will come. So, you have y 3 and y 4, this is 1 1 0 and 0. So, y 3 is 0, but y 2 coefficient is this. So, if I calculate it and write down after row manipulation, I will obtain 1 3 0 1 minus 2. And for this case x 2, this will be 2 0 1 0 and 1. So, basically this is 1 and this is 0, y 2 was the entering vector. So, z j minus c j, if you calculate, minus 1 0 0 and 1. Again for this particular case, your z j minus c j is less than 0. I have only one negative value. So, therefore, this one is entering is this one. Calculate the ratio b by y value. Here it is 1/3, this will be infinity. So, we cannot consider. Therefore, your departing variable in this case will be x 3. So, your x 3 will go out and x 1 will enter into the basis, and your pivot element is this. Pivot element is 3, this one. So, I hope it is clear. This is the pivot element and x 3 will go out and x 1 will enter in the next iterative table. So, let us formulate the next iterative table. In the next iterative table, x 3 has been replaced by x 1 and this is x 2 is already there. So, this will be y 1 y 2. The coefficients of the objective function c j's are 1 1 0 and 0, x 1 x 2 both are 1. So, if I am writing, it is 1/3 1 0 1/3 minus 2 by 3, and for this case it is 2 0 1 0 and 1. If you calculate the z j minus c j values, you will obtain 1 minus 1 0, 1 minus 1 0, in this case 1/3 minus 0 1/3, this is equals minus 2/3 plus 1. So, it is also 1/3. So, for this particular case, if you find your z j minus c j is greater than equals 0 for this problem, your z j minus c j greater than equals 0 for all j. But what happens? X 1, if you see, value of x 1 is 1/3, which is not integer. Since x 1 is not integer, therefore, I have to formulate now the Gomorian constraint from this and this one. I have to formulate the Gomorian constraint. If you write down, so now basically I have to formulate this g 1 equals this thing. Your corresponding to this equation I can write down as 1/3 equals x 1 plus 0 into x 2 plus 1/3 into x 3 minus 2/3 into x 4. The corresponding to the row where x 1 is having fractional value. So, x 4 has the most negative coefficient in the mixed fractional part. So, using this Gomorian constant now g 1, this now I have to calculate. So, your S 1 will be equals to, in place of g 1 I am writing S 1 minus f 1 0 plus f 1 3 will come only f 1 3 x 3, because this is the positive one. If you remember, I have told it has two parts, y k j x j, where j belongs to r plus is y k j greater than 0. So, y k j is greater than 0 on this case here only. Similarly, your y k j is less than 0 for this, and for that one it will be j belongs to r minus y k j less than 0 where the coefficient will be f k 0 by f k 0 minus 1. So, this is f 13 into x 13 plus f 10 by f 10 minus 1 into f 14 x 4. So, once I am getting these values, now I can calculate the values. F 10 is 1/3, this one. So, f 10 is minus 1/3, then f 13 is 1/3 x 3 plus 1/3 by 1/3 minus 1 into f 14 is minus 2/3. So, you are writing minus 2/3 into x 4. So, I hope now it is clear how we are making using this Gomorian constraint over this problem. For this case, the equation at first I wrote it like this and it was minus f k 0 plus these things f 13 x 13 f 10 by f 10 minus 1 into f 14 into x 4. So, now I am putting the values of f 10 which is 1/3, f 13 is 1/3 and f 14 is minus 1/3. So, that you will obtain S 1 equals this. By simplification, I can write it as minus 1/3 x 3, sorry, this will be x 3. This is not x 13, this will be x 3 and this is x 4. So, minus 1/3 x 3 minus 1/3 x 4 plus S 1 equals minus 1/3. So, your Gomorian, using the Gomorian slack variable S 1, you are adding this constraint. So, now on this particular matrix, on this particular table, you have to add one more row here, where S 1 will be entering into the basis. So, once S 1 is entering into the basis from here, that means these rows will remain as it is, only this row will enter and one more variable S 1 will come. So, in the basis you will have x 1, x 2 and S 1. So, S 1 means corresponding to this row, which we are adding as a new Gomorian constraint, which we have done earlier. So, this will be y 1, y 2 and S 1. Cj values are 1, 1, 0, 0, 0. S 1 corresponding to slack variable S 1, coefficient in the objective function is 0. So, x 1, x 2 is 1, 1, this is 0. So, I am writing there will be no change on the previous table for first two rows, that is 1/3, 1, 0, 1/3, minus 2/3, minus 2/3, S 1 is 0, second one is 2, 0, 1, 0, 1, 0 and third one will be b value is minus 1/3, then it is x 1, x 2 is not present, coefficients will be zeros. For x 3 it is minus 1/3, for x 4 it is minus 1/3 and corresponding to S 1 coefficient is 1. So, you are writing the coefficient as 1 over here. Now, once you are calculating this, calculate the Zj minus Cj value. First one will be 0, 1 into 1 is 0, second one will also be 0, third one is 1/3, fourth one will be, will also become this fourth one will be minus 1/3 into 1, 1 minus this. So, it will remain 1/3, 1 minus this and then this value will be 0. If you see here, your Zj minus Cj, this is greater than equals 0 for all j, but value of the one of the basic variable is negative here. So, already we have done this type of problems. Whenever I have the negative value in the basis. Therefore, I will use the dual simplex method, which we have discussed earlier. I hope you remember that thing, that in the dual simplex method, first I have to find out what is the departing vector, the variable which is going out, that will be the departing vector, and from there I have to calculate what is the entering vector. So, in this case you first now use your dual simplex method. So, once you are taking the dual simplex method, this will be the outgoing vector, and from here you will find that this is the entering vector. I am not discussing again the dual simplex method here, since already we have done this type of problems earlier. So, this is your outgoing vector, departing vector is S1, entering vector is your Y3 or X3. So, your pivot element is this. Since your pivot element is minus 1/3, that means now I have to make this element as 1 and all other elements on this particular column as 0. So, if I take the next one, in that case your S1, if you see this table, on this table your S1 will be replaced by X3. So, in the basis for the next table you will have X1, X2 and X3. So, let us write down now these three, X1, X2 and X3. This will be Y1, Y2 and Y3. Your CB values will remain as it is 1, 1, 0, 0, 0. So, this is Cj, not Cb, this is Cj, and Cb values in this case will be 1, 1, corresponding to X3 it is 0. So, basically I have to make these as 1 and these elements as 0. So, this will become now, after performing the row operations, this will become 1 0 0 1 1 minus 3. I have to make the other elements such that on Y3 the components are 0. So, you will obtain in the first row as 0 1 0 0 minus 1 1, and for this case you will obtain 2 0 1 0 1 3. Your Zj minus Cj value will be 1 minus 1 0 in that case. For the second one 1 minus 1 0, for the third one 0 0 0 minus 0 0, for the fourth case minus 1 plus 1. So, 0 plus 0 minus 0 it is 0. For this case it is 1 plus 3 4, this is 0. So, 4 minus 0 this is 4. So, if you see here your Zj minus Cj is greater than equals 0 for all j, and the basic variables which are x1, x2 and x3, value of these basic variables are integers. Therefore, you have obtained the optimal solution, which is also satisfying your feasibility condition. So, I can now write down from the basis my optimal solution of the original problem is x1 star equals 0, x2 star this is equals to 2, and my z star this will be equals to 0 into 1 plus 0 into 2, this is equals 2. So, this is the solution of the original problem. So, I hope it is clear to you now. Whenever I have mixed integer programming problem, where some of the variables can take only integer values, some can take either real value or integer value. So, in that case my procedure should be first solve the problem without ignoring the integer constraint. After that, check the solution and find out whether there is any non-integer solution is there in the basis or not. If there is any non-integer solution corresponding to that non-integer variable, you formulate the Gomorian constraint, you add one more constraint which we are saying as Gomorian constraint, and in that Gomorian constraint and corresponding Gomorian slack variable will be added in the basis. So, one more row will be added in the next iterative table, and then find the entering vector and departing vector using the dual simplex method, and repeat the process until you are obtaining the optimal solution. So, hope that it is clear how, if I have a mixed integer programming problem, how to obtain the solution.